So today we have the Merging Technologies webinar by Marcus Hall on 3D printing, robots and reality capture. I'm Kirsty Mackey, a reality capture specialist at Global Survey, and I'm going to be hosting today. So a little bit of an agenda for you guys. First of all, I'm going to go through the Archer & Z conference because that's the next event we have coming up. Then I'm going to introduce you to Marcus. He's going to give his webinar. It's about half an hour long. And then if you have any questions that you want to ask, just put them through in the questions tab in the GoToWebinar panel on the side here, and we'll answer them at the end. So our Archer & Z conference is coming up at the end of this month. We're already in March. So March 22nd, it's a Friday. It's at Sidamar Hotel at Auckland Airport and will be from 8:30 till 4:30. It's a whole day all about reality capture. So what more could you want? The tickets are 250 plus GST. We've got a range of speakers from lots of different backgrounds. Dr. Catherine Sam will be giving the keynote speech at the beginning of the day. And then we've got loads of different speakers from digital, surveying backgrounds. It's really, really exciting. So I hope you can be there. We've got loads of really cool talks that are going to be part of it. So from mobile mapping to reality capture and visualization, a bit of VR. There'll be a bit of GIS in there as well, and online hosting for point clouds. And then there will also be a panel at the end, which I'm particularly excited for, which will be about, is Aotearoa ready for the digital age? So that'll be quite exciting with a focus all on reality capture. So if you want to hear anything else about that, it's all on our website. Just type in Archer & Z to Google, and you can also buy tickets online or email us at info@globalsurvey.co.nz. So Marcus Hall, super excited to have him speaking with us. He has done a webinar on the 3D printing and the robots before, but he's going to show us today about how it's developed because there's been lots of changes. So I actually worked with Marcus at Beca when I was there. He's super experienced in all things surveying and laser scanning. He did a Bachelor of Surveying at the University of Otago and has over 20 years experience in surveying. And one thing I would definitely remark about him is that he's a tech enthusiast. I remember him doing some of the printing when I was at Beca, and he always sounded very passionate about it. So without further ado, I'm going to pass over to Marcus.
Thanks, Kirsty. Just get my webcam going.
Great, we can see everything all good there.
Cool, excellent. Kia ora koutou, e ngā kaimahi pakahi, nau mai haere mai. Good morning, everyone. So as Kirsty said, I'm actually a licensed surveyor at in the Hamilton office. Been here for about 7 years, with 20 years in the industry. So a good chunk of my career was spent overseas on some significant construction projects in the UK and Australia. For the most part, it's been a career that has been defined by the management of the usual survey and civil related endeavours. However, recently it's taken a slight change of approach and has been driven by profound enthusiasm for addressing industry challenges. And it's been a journey marked by a commitment to innovation. So this passion has led me to pursue new ways to leverage advanced data acquisition technologies such as 3D laser scanning and other measurement sensors to open up new work fronts and enhance safety, accuracy and efficiency of our survey processes. As a technology enthusiast, I find the recent advancements of our field incredibly exciting. This enthusiasm is not just limited to adopting new advanced reality capture tools, but extends to inventing new ways to use the tools we have at our disposal and thereby enhancing them. So in 2016, the world saw the launch of the BLK 360, the smallest commercial 3D scanner ever. This technological advancement, combined with the spread of other technologies such as 3D printing, open source hardware and software, cheap sensors, and a vast array of adaptable and compatible components, has opened up a realm of opportunities. Whether you need a quick solution or something bespoke that's not available off the shelf, the merging of these technologies has extended the reach of reality capture, limited only by your imagination. Developing new methods to apply measuring devices like a 3D scanner in hazardous situations, tight spaces, and environments that we want to avoid, but where the data gathered is useful, provides significant value, and is where the survey industry can discover new possibilities. It is this passion for innovation that Beca has supported me with to develop PyPy, our in-house survey robot, a project that represents the culmination of significant effort and creativity. Today, I'm pleased to share with you the journey of PyPy so far. I'll run through some of the history, how we got here, talk about some of the design considerations and PyPy's features, some of the things we learned along the way, trials and tribulations, and some typical project examples of how it's demonstrated value, and a bit about what the future might look like with this type of technology. So the story of PyPy started with dangerous environments. Unsurprisingly, the request for measurement data in environments that are not safe for our people to enter is increasing, largely due to our ever-improving health and safety culture. Our perception of what defines a dangerous environment has changed, and we no longer treat many of these areas like we used to. So a few years ago, when I was struggling with options to survey these environments safely, I found it surprising that the survey industry was at the time limited in options to complete measurement surveys remotely out of line of sight when ground-based operations were best suited. So aerial drones or unmanned aerial vehicles had the skies covered, tremendously successful in many ways, primarily allowing the surveyor to stay in a place of safety while the drone does its work. But there wasn't much going on in terms of a robotic vehicle that could measure stuff remotely. So the opportunity presented itself to our survey team. One of Beca's highway structure inspectors was undertaking a routine inspection of a culvert which was approximately 40 metres long and 2 metres in diameter. The culvert had significant fractures in lots of different places and significant shape distortion could be seen, but it was unclear how bad it really was and if the deformation was still active. The culvert sat under a highway that provided the only access to a remote part of the coast. The inspector took a couple of photos and quickly exited the culvert. This was immediately brought to the attention of my colleague Max, a structural engineer in our Tauranga office. There existed only a few records on the culvert, which was not surprising for the remoteness and the age of the structure. But due to the extent and the location of the damage, Max needed someone to go back inside and collect more information, but had no means of gathering this data safely. Max posed the question to me, can you accurately measure this culvert without going inside? So what did accurately measure mean? It meant 3D laser scan the entirety of the culvert to create a digital twin of it to within plus minus 10 mil. How would this help Max? Well, he could understand the size of the problem, the shape of the pipe, baseline the measurement against future measurements to understand movement over time, and make informed, calculated engineering decisions from actual data. So it sounded like Max needed some kind of contraption that takes this new 3D scanner, the BLK, into a culvert. An idea had formed, but I thought I'd better not tell anyone what I plan on doing with this new scanner. Initially, the PyPy project began as a small endeavour, with each iteration intended to be a standalone effort. However, as the idea progressed, it gained more interest from the clients and support from the business, this allowed us to further develop the concept, making it increasingly useful and valuable. It was like pulling a thread. The more we advanced, the more potential we uncovered. With the help of 3D printing technology, we were able to rapidly iterate on prototype designs and enhance the functionality of the robot over time. The Mark I version was basic, a trolley pulled by a rope from the downstream end of the culvert every 3 meters. It was rudimentary, and the Wi-Fi range of the scanner posed a significant challenge, but it provided the data we needed. With Mark II, we constructed a 6-wheeled robot, powered, mostly 3D printed, and added a scissor lift for the BLK to protect it, along with a live camera feed. Mark III and IV were further iterations where we focused on improving aspects such as waterproofing the motors and upgrading the radio and video systems. It was only in the last year that PyPy was envisioned in its current form. So from this to this. So I guess there are some similar features that carried through from the first motorized version to today's model, but PyPy today is a significantly enhanced and more capable machine. So PyPy's features listed here are the sum of several years of trials and successes and failures on design on actual projects. So I mentioned the Wi-Fi signal. Now that PyPy had an upgraded radio system up to 10 kilometers in range, we couldn't be constrained to a 30-meter range to control the scanner. Excuse me. So we designed a mechanism to use the scanner's onboard scanning functionality. This relies on the scanner rotating back to the exact position. Funnily enough, or not so funny, the new BLK 360 accrues rotationally, and that it doesn't return back to the same position, which means back to the drawing board. Lighting was a major consideration for these dark spaces, and the more lighting you can get, the better, improving the inspection imagery, colorization of the point cloud, and all-round quality. Point clouds are really challenging to register in these environments. The robot has an onboard autopilot and a high-performance control system designed for advanced drones and robots, enabling navigation and autonomous capabilities in various unmanned vehicles. I'll touch on what this means a bit later. Another feature of our robot is the Raspberry Pi companion computer running the robot operating system and acts as a mini brain for the robot and helps it to understand and interact with the world and communicate and perform tasks autonomously. This allows the PyPy to do so much more. So the companion computer relies on inputs from the various other sensors, the 2D proximity lidar, and the rangefinders, the GPS, and so a significant learning through this development was also the quality of the cameras and what you can see if you're navigating out of line of sight. So the central objective in the design of PyPy was to incorporate a scanner such as the Leica BLK 360 as an integral component of the system. So we literally started with a model of the scanner and designed PyPy around it. The development of this robot had to complement the scanner's dimensions and functional requirements. A common query I received, and in fact something I've constantly asked myself, why an off-the-shelf robot hasn't been adapted for this purpose. And the rationale remains fairly steadfast to this day. Rather than affixing a scanner to a pre-existing robotic platform, it was important to ensure that the scanner was not merely an attachment, but a protected, integral feature. This approach allows the scanner to be securely stowed and easily deployed when necessary. Moreover, the design flexibility to remove the scanner cradle ensures that the robot's cargo bay, which can be adapted for various other equipment as needed, enhancing the versatility of PyPy for multiple survey tools and applications. So PyPy's construction prominently features 3D printed components. A project of this nature, leveling 3D printing technology, would have been impractical 15 to 20 years ago without significant dependence on specialist manufacturers and likely prohibitive cost. The use of 3D printing technology has been pivotal. It has facilitated the rapid prototyping, allowing us to assess the fit, the durability and performance of components, thereby quickly iterating through design modifications. This use of the use of robust plastic filaments such as polycarbonate and nylon means the parts we produced are not only quick to fabricate, but also remarkably resilient. 3D printers have come a long way, particularly in the last year or so. The speed is a major improvement. Now they are capable of up to 6 times faster. This video, the speed looks almost unreal. While these 3D printed materials don't match the strength of aluminium or injection molded plastics, they meet the necessary load bearing requirements for each specific application within the PyPy. For components requiring finer detail, resin printed was utilised for precision. To enhance the structural integrity, the outer shell of PyPy was reinforced with layers of carbon fibre. So PyPy's strength was a critical design factor due to the high torque output of its drive system. Earlier models of PyPy lacked the necessary power to reliably navigate challenging environments. The current iteration is equipped with 6 200mm diameter wheels, each driven by really high torque DC motors, allowing it to overcome most obstacles with ease. With a total weight of 25 kgs, PyPy boasts approximately 30 kgs of pulling capacity. This robust construction makes it capable of carrying advanced scanners like the P40 or the RTC 360. In fact, probably any modern scanner. While it's not designed for stair climbing with such heavy payloads, PyPy could perform reliably on moderate terrains. Developing a single robot capable of functioning effectively across all environments is a major challenge. The most viable approach was to strive for versatility within a limited range with a specialised in inspection and measuring. The concept of adaptability across multiple environments stemmed from insights gleaned from the past iterations. Initially, the focus was on designing for culverts, but demands emerged for surveys of underfloor spaces, for example. Thus, the capability to adjust its height between 300 to 500 mil proved invaluable. This enabled the robot to enter to maintain elevation to navigate through moderately flowing culverts or minimize its profile when operating beneath buildings. And an additional benefit of the system was its capacity to re-level itself in the scanner if necessary. Naturally, with these things, the more data that becomes available, engineers develop an increasing appetite for it, and the demand for higher quality surges. To meet this need, a 4K gimbal camera was introduced to facilitate more detailed inspections. The interesting thing is, now we have a programmable gimbal camera, much of the inspection can be automated. PyPy has been utilised in several projects where assets have deteriorated to the point that it is no longer safe for inspection engineers or surveyors to enter these confined spaces. The environments are typically culverts, and on several occasions, these projects become monitoring exercises where we establish a baseline set of measurements and measure if there is any change over time. The example I talk about now, there was over 140 metres of culvert pipes and structure that needed to be measured and inspected under State Highway 2 in a real-world scenario where significant slips had affected a major state highway. The engineers required inspection video and spatial data to understand the performance criteria of these culverts and also try to figure out where the source that was causing ongoing erosion. This is a time-lapse video of the robot scanning inside the culvert, and it's all completely manually done, but out of line of sight. The scanner is activated every 5 meters or so, and as mentioned, it's a challenge in these environments to register the cloud. And in this example, the sweeping nature of the culvert was handy to provide some certainty about longitudinal positioning of the cloud. We established control at the ends of the run only, so we have to accept some inaccuracy in the middle, but with decent 50% overlap, the cloud-to-cloud solution can be reasonable. This is just an output from the scanning operation. As I mentioned, it takes quite a bit of effort for the cloud-to-cloud. You can see the fixed control at each end. This emergency job, this is a new job, another culvert. So this emergency job really epitomised the value a tool such as PyPy can deliver. A culvert that was at risk of imminent collapse, too dangerous to enter under confined space. Accurate data was needed to confirm the engineering solution. The engineers needed accurate information of the inside of the culvert to support the fabrication of a steel sleeve. We were able to measure the entire culvert to within plus or minus 10 mil, providing certainty around what the minimum cross-sectional profile was. The hard data meant that the engineers made an informed decision on the design being fit for purpose and have full confidence that the sleeve will fit, avoiding unnecessary risk to personnel and delays to road users. In this example, PyPy was used to gather data inside a heavily corroded warehouse dispatch building, unsafe to enter. This building was near collapse, needing structural intervention. However, no one was allowed in it. We were able to provide accurate information for the structural engineers to enable the fabricators to fit tailored steel beams at the correct angles, meaning they don't have to spend as much time trying to fit the beams on site. We're able to identify other significant structural issues the client and engineers were not previously aware of as well, with all the extra data gathered. In this example, we used PyPy to access an underfloor area to pick up visual information about the condition of the piles as well as spatial data for which no record existed. These spaces are commonly dumping grounds for all sorts of stuff and can be quite often contaminated. So we had to be really careful about cleaning the robot off when it re-emerged. Cable ducts can be cables and ducts. It can be a real challenge, and you need to be really careful about not getting tangled up. So through the various projects, we've discerned direct advantages of employing robotic survey capture. Time savings, for instance, this twin culvert example was completed in approximately 3 hours. So conducting this conventionally would likely be very challenging, if not impossible. Additionally, the costs associated with setting up confined spaces and rescue equipment would likely outweigh the benefits. So de-risking the project with the project engineering solutions. So by utilizing actual data, we eliminate the guesswork and provide reliable, repeatable, and accurate measurement data. This assurance removes any doubts regarding the hydraulic system performance. We managed to unearth insights, so our approach has enabled us to gather insights that would otherwise have been overlooked. And of course, enhance safety. Eliminating the need to physically enter these spaces mitigates the risks associated with the hazardous environments. This alternative option provides peace of mind, especially in environments where safety concerns are paramount. So PyPy is controlled by what is called a ground station, the same as those utilised for unmanned aerial vehicles. So this serves as the central hub where PyPy's cognitive processes and autopilot functionalities operate. So displayed here is to the top is a flight plan that is presented on the ground station, allowing users to outline a series of waypoints for PyPy to navigate to autonomously and conduct scanning operations. So operating a scanner remotely via manual robotic control is really useful and brings great value. However, it's clear the future lies in autonomy. So this shift to autonomy holds significant implications for productivity, enabling surveyors to delegate routine tasks in repetitive environments to robots. Concurrently, they can focus on tasks such as installing control marks, while the robot independently conducts spatial data capture. These technologies have great potential for asset management. AI and asset monitoring have attracted a lot of interest from various industries. The creation of automated systems that can collect, store, analyze, and report data about assets that are repetitive and linear, such as roads and street furniture, culverts or tunnels, has become a real topic of interest. The combination of robotics, reality capture, and smart AI analysis systems will change the management of assets from a reactive system to a proactive system that extends the life of an asset and provides the best value for the public who depend on it. So PyPy started with a very simple concept: how to conduct a survey remotely while the surveyor remains in a place of safety. This became achievable through the convergence of various technologies, which allowed us to shift our perspective. So as we adapt to this new way of working, our perspective shifts, allowing us to uncover opportunities that we hadn't anticipated before. Navigating hazardous environments will persist as a challenge for our business, posing risks to project outcomes and the safety of our personnel. While it's anticipated future regulations will continue to disrupt the conventional approaches embraced by surveyors and engineers. Surveying has a really rich traditional heritage, yet is also closely linked with the progress of technology. So balancing the old with the new is key to capturing emerging opportunities and staying competitive in this constantly changing environment. Thanks very much.
Awesome, thank you very much. That was fantastic. So we've got a couple of questions here. If you can just pass the control back to me. Awesome, you guys can see that. So, first question, how much experience did you have with 3D printing before starting on the endeavor of creating the robot, and how long did the first robot take?
Yeah, I picked up my first 3D printer. Actually, it was one I built It was a $300 kit, and so I kind of started from the bottom, and I had about, I'd say, close to 10 years experience, I think, just dabbling with 3D printing and just gaining experience. And the robot, the first robot, it took about a month. So it was one of those quick,
wow.
yeah. So it was a very, very busy month of lots of, late nights. So in a printer that was running hot pretty much 24 hours a day. But it was a fairly limited budget. I think it costs about probably $1,500 in bits and pieces. But it was, we had a deadline, and quite often it was a deadline that progressed things to the next stage.
I was thinking a month was not that long to create a robot that was functional. That's pretty awesome. So how often do you use the PipeEye for projects?
Yeah, I mean, there's a lot of opportunity. I mean, we could be using it every week, I think. And it's just, I guess, it's just being able to, I guess, pass on the reins to other people to use it. It's really got to that point where I need to hand the keys over and teach someone else how to use it. But it's, yeah, regularly it has jobs come up. So at the moment it might be maybe a couple of times a month, but it could easily be a lot more if we enabled other people to be skilled up in its use.
Awesome. In terms of being skilled up on its use, there was actually a question just now, which is quite interesting. So Brenton's asked, I noticed there's no tether line on the PipeEye. What's the process of recovering the equipment if the unit fails or is entangled? Are there any built-in fail-safe features? I can imagine that's definitely part of the training.
Yeah, no, there is actually a tether hook underneath, and it's really a case-by-case situation. Where, yeah, we have designed a retrieval system, which is like a winch. If we were going, into a really deep culvert that had lots of obstacles and just unknown kind of conditions, we would certainly tether it up. But on some of these shorter runs and some of the shorter culverts, we're very comfortable that it's a very unlikely situation that it's not going to return. So the system is very, very reliable. I say that touching wood, but yeah, we haven't had a situation yet with all the testing we've done.
Awesome. So I've got a few more. There's how does the gimbal camera enable the automation of the inspection aspects? You mentioned about putting on the higher resolution camera, and then you said that it would automate it a bit more. I remember that slide.
Yeah. So I mentioned we have a Raspberry Pi. So and something I didn't mention was another bit of technology that came out in the last few months, or maybe the last 6 months, was ChatGPT. Now I'm not a computer programmer. I've never done any coding. However, when ChatGPT came along, it actually enabled me to start building small scripts. So the Raspberry Pi takes Python scripts, and so you can build a script that where the companion computer can tell the autopilot to operate all the servos and all the connected peripheral sensors to perform certain functions. And so we can actually program a gimbal camera, for instance, if we're in a culvert, to you know, look 90 degrees and then take record information in a uniform fashion. So really, yeah, there's obviously lots of different, and that might depend on the environment you're in, on what sort of script or what sort of operation you need it to perform.
Okay, so I've just got 2 more. Got some nice comments in the questions tab here, saying congratulations on the amazing solution and great presentation from Lyndon Teffler, by the way. So 2 more questions. Have you thought about putting targets on the robot to fix targets? You were mentioning cloud to cloud through one of the longer tunnels. Did this work? Have you tried it?
Sorry, putting targets on the robot to fix in the tunnel, is it?
So as in, I think it's more like, because you've got the ones at the beginning and the end that you were speaking about. So I think this question is getting at, as you go through the tunnel, if you were to stop because you're doing static scans and use ones that are inside there.
Yeah, I've absolutely thought about that, and it's not a solution I've come up with, other than potentially having a companion vehicle that straddles. Just this is an insight into how my brain works, but straddles the inside of a tunnel, and potentially above the robot, and has targets with it. But yeah, it's definitely something that would help the servo solution.
Looks like Becca's going to end up with a fleet of robots.
Yeah, no, but that's still on the drawing board, that one.
Okay, and last question. I want one, where can I get one? That's from Quentin Gilkinson, so maybe I can put you guys in touch after this.
Yeah, by all means, give us a call.
Wow, thank you very much for that, Marcus. Yeah, so I see there's no more questions coming in now, so I think we'll end there. Yeah, thanks for everyone who attended. We had quite a few of you here today. So just a reminder, our next event will be the ArchNZ User Conference, and you can sign up on our website. So thank you, everyone. Bye.
Thanks.